Before there was structure, before there was light, there was silence. Not the silence of a quiet room, nor the stillness between breaths, but a silence more complete, the absence of time, of space, of anything that could carry a sound. Then, creation unfolded. Galaxies bloomed. Stars ignited. Black holes yawned open, swallowing light and time itself. The universe became a stage of violence and beauty, a place where every act of creation carried with it an echo of destruction. Among these echoes are events so immense that they escape imagination. Explosions not measured in fire, but in the rearrangement of space itself. Eruptions not of sound, but of invisible shock waves that ripple across millions of light years. Astronomers have catalogued many forms of cosmic violence. The death of a star in a supernova, bright enough to outshine an entire galaxy for a moment in time. The collapse of a giant star into a black hole, tearing its own heart apart. The sudden flare of a gamma ray burst, releasing in seconds more energy than the sun will in 10 billion years. But in the depths of the universe, there is something greater, something that dwarfs even these titanic events. In 2020, astronomers peering into the Ophiuchus galaxy cluster revealed evidence of the largest explosion ever recorded. Not a supernova, not a gamma-ray burst, not even the final cry of a dying black hole. This was different, stranger. An outburst so vast it carved a wound 1.5 million light-years across into the plasma of a galaxy cluster, a cavity so enormous that our Milky Way would disappear inside it, leaving room to spare. The energy released was staggering, hundreds of millions of times greater than a supernova, thousands of times greater than the most violent gamma-ray bursts. For a brief moment in cosmic history, a single black hole unleashed more power than the combined radiance of entire galaxies. It was not fire, it was not light. It was the fabric of reality itself being pushed aside, as though the universe had exhaled with unimaginable force. And yet, when astronomers discovered it, the event was long over. The fury had subsided. Galaxies circled calmly, as though nothing had happened. Only the scar remained, a silent testament to an eruption beyond comprehension. What could drive a black hole to such violence? How could an object defined by its hunger become the engine of the largest explosion since the dawn of time? And what does this tell us about the nature of galaxies, clusters, and the cosmos itself? The universe has always hidden its truths in silence. In the cavity of Ophiuchus, that silence has been broken, and the question lingers still. The story begins not in silence, but in a sea of heat. Between the galaxies of the universe lies no empty void, but a web of matter, diffuse, incandescent, invisible to human sight. In the densest regions, where hundreds of galaxies huddle together, in clusters, this matter is trapped in gravity's embrace. It swirls as a plasma hundreds of millions of degrees hot. It radiates not in light or color, but in X-rays. These clusters are the largest gravitational structures held together since the dawn of the cosmos. They are islands of universes within the universe, cradling galaxies, stars, and black holes in their vast tides of dark matter. To understand them is to glimpse how cosmic architecture is built and broken, And so, astronomers point their instruments toward these clusters, peeling back layers of radiation the human eye cannot see. Orbiting high above Earth, the Chandra X-ray Observatory drifts in silence, its mirrors polished to focus the most elusive rays. Alongside it, the European Space Agency's XMM Newton telescope surveys the same skies. On the ground, radio observatories in India and Australia listen for longer echoes, the low-frequency songs of cosmic storms. Together, they form a choir of machines tuned to frequencies beyond human senses, translating the language of the universe into data. In 2016, one such survey turned its gaze toward the Ophiuchus galaxy cluster. To the naked eye, Ophiuchus is a dim region of stars tucked between Sagittarius and Scorpius, but behind them, more than 390 million light-years away, a cluster of galaxies lies, bound in a common halo of plasma. It was here that the first anomaly appeared. The data hinted at a cavity, an emptiness carved into the plasma surrounding the cluster's central galaxy. Such cavities were not new to science. Astronomers had seen them before, scars left by the outbursts of supermassive black holes. As jets of energy shoot from their poles, they displace the gas around them, blowing bubbles that can last for millions of years. These cavities are clues, fossils of violence long past. But this cavity seemed different. It was too large, too sharp, too improbable. To some it looked like an error, perhaps a flaw in the analysis or a trick of noise. The idea that a black hole could gouge out a void so colossal strained credibility. Years passed. More observations were gathered. XMM Newton confirmed the shape. The giant meter-wave radio telescope in India traced the contours in radio frequencies where relics of ancient jets still whispered. The cavity was not illusion. It was real. When the calculations were made, the numbers silenced all doubt. The Adam void stretched across space for 1.5 million light-years, 15 times the diameter of our Milky Way. To hollow it out required an energy release of unimaginable scale, the equivalent of detonating hundreds of millions of supernovae. It was, in effect, the single largest known explosion since the Big Bang itself. The culprit was clear. At the center of the cluster sat a supermassive black hole, the kind that anchors nearly every galaxy. Its mass was hundreds of millions of suns, yet its appetite had turned outward. In a fit of fury, it had driven jets of plasma so violent that they bored a wound through the cluster's hot atmosphere, flinging matter aside on scales dwarfing entire galaxies. And yet, this eruption was not recent. By the time human eyes saw it, the event was already ancient. Its violence long subsided. The jets had cooled. The cavity remained, preserved like a fossilized ripple in the sea of time. Simona Giacintucci of the Naval Research Laboratory, one of the scientists leading the study, recalled the disbelief. The size of this cavity is extraordinary. It was an understatement. Nothing on record compared. Even Maxim Markovich of NASA's Goddard Space Flight Center, a veteran of X-ray astronomy, acknowledged the scale as staggering. For decades, astronomers had theorized that black holes could shape their galaxies through feedback, injecting energy into the surrounding gas, slowing star formation, regulating the life cycles of galaxies. But here was feedback on a scale so extreme it rewrote the limits of imagination. This was not gentle regulation. This was annihilation. The finding forced a new reckoning. If black holes could release energy of this magnitude, what role had they played in the early universe when galaxies were still young? Could eruptions like this have sculpted entire clusters, bending the growth of cosmic structures? Could they have been architects, not just destroyers? In Ophiuchus, the plasma still glows, faint and constant, as if nothing unusual had occurred. Galaxies continue their silent orbits, their stars unaware of the storm that once swept past. Time, in its vast patience, has smoothed the scars. Yet the cavity endures, a shadow carved into the fabric of matter itself, a reminder that the universe is neither stable nor tame. For the astronomers who revealed it, the discovery was more than numbers and maps. It was an encounter with scale, with violence beyond comprehension, with the humbling realization that even the most destructive forces can vanish into quiet, leaving only silence behind. The Ophiuchus cluster remains suspended in the night sky, 390 million years removed. The explosion that carved it happened long before the first mammals walked the Earth, before the continents had taken their present form. And yet, through the lens of modern instruments, its echo arrives now. A ghost, a violence preserved across eons. The discovery was only the beginning. The cavity raised questions that continue to haunt. What triggered the eruption? How does a black hole, a region defined by its hunger for matter, decide instead to unleash such ferocity? And if such events are possible in Ophiuchus, how many more remain hidden in the cosmic deep, their scars awaiting discovery? The scientists could measure the size, calculate the energy, map the shape, but the why, the reason a black hole could explode on such a scale, remains one of the enduring mysteries. And so the chapter closes not with resolution, but with awe. In the heart of Ophiuchus, humanity has glimpsed a scar that dwarfs comprehension. The universe has revealed one of its oldest and greatest explosions, and then fallen silent again, leaving us with nothing but the void and our own questions echoing back, an immense ocean of silence. That's how we once pictured the space between galaxies. A static, silent void stretching across millions of light years. But this emptiness, we've come to understand, is an illusion. The space between galaxies is not a vacuum. It is filled with a thin, tenuous gas, a superheated plasma that is almost invisible to us. It is this medium, the intra-cluster medium, that carries the whispers of cosmic history. For decades, astronomers have been studying these massive congregations of galaxies, known as galaxy clusters. They are the largest gravitationally bound structures in the universe, veritable cities of stars and gas held together by the immense pull of gravity and dominated by the mysterious force of dark matter. By using specialized instruments like NASA's Chandra X-ray Observatory, scientists can peer into these cosmic structures, mapping the distribution of the superheated plasma that fills them. This plasma, heated to tens of millions of degrees, emits light in the form of X-rays, giving us a window into the otherwise unseen workings of the cluster. It was within one such cluster, the Ophiuchus galaxy cluster, that a startling discovery was made. Astronomers were sifting through data, searching for the subtle patterns of energy and matter, when they noticed an anomaly. In the hot plasma surrounding the cluster's central galaxy, there was a strange, unexplainable indentation, a cavity of immense proportions. It was no ordinary hole. Its sheer size was a testament to a force so powerful it had literally carved out a section of the intracluster medium. The size of this cavity was so vast it defied all previous observations. For the astronomers studying the data, it was a moment of profound revelation and deep confusion. This was not a scar left by a single supernova. 1,000, even 1,000,000 stellar explosions would not have been enough to displace so much gas. No, the scale of this event was cosmic. The source of this unimaginable power was quickly traced to the supermassive black hole at the heart of the galaxy. Black holes are often imagined as cosmic vacuums, simple devourers of light and matter. But in their most active states, they are also engines of immense power, capable of launching powerful jets of plasma from their poles. As a black hole feeds on surrounding gas and dust, this material forms a swirling accretion disk that spirals inward, heated to searing temperatures by friction and intense magnetic fields. It is from this disk that the black hole draws its power, not to consume, but to create. It funnels energy into twin, oppositely directed jets of charged particles, launching them into space at nearly the speed of light. For millions of years, these colossal jets had been punching through the dense intracluster medium like a drill boring through rock. They had swept aside billions of solar masses of gas, leaving behind a vast, hollow void in their wake. The cavity was a negative image of the black hole's power, a perfect silent record of a violence that occurred hundreds of millions of years ago. The shock was not just in the discovery itself, but in the sheer scale of it. Astronomers had seen such cavities before, most notably in the M87 galaxy, but this one was different. It was 5 times wider than the one caused by the M87 black hole, making it the largest cosmic explosion ever observed. The energy released to create such a void was staggering, hundreds of millions of times the energy of a typical supernova. This wasn't a brief, powerful burst. This was a sustained cosmic outburst, a long, relentless act of creation and destruction. It revealed that black holes are not just passive entities at the center of galaxies. They are active, dynamic engines that shape their environments on a cosmic scale, capable of influencing the fate of an entire galaxy cluster. The initial discovery, led by a team using the Chandra X-ray Observatory, was just the beginning. Other observatories were brought into the fold to confirm the findings. Radio telescopes, which are sensitive to the synchrotron radiation produced by the black hole's jets, searched for the remnants of the powerful beams. They found them faint and old, a testament to an ancient, ongoing process. Infrared telescopes looked for evidence of dust and gas being pushed away by the shock wave, while optical telescopes observed the galaxies that might have been affected by this colossal event. Through these combined observations, scientists began to piece together a timeline. By measuring the size of the cavity and estimating the speed of the expanding shock wave, They could calculate when the explosion occurred. The timeline stretched back hundreds of millions of years, placing the event in a distant cosmic past. This discovery provided a crucial piece of the puzzle in the cosmic energy feedback loop. It showed how a supermassive black hole at the center of a galaxy can prevent the surrounding gas from cooling and forming new stars. This process, a form of cosmic thermostat, can effectively shut down star formation, leaving a galaxy with a vast, silent, and ancient population of stars. It also changed our perception of the universe. It revealed a hidden layer of violence and power, a force so immense that it can literally shape the cosmos on a scale of millions of light years. It connected the physics of the infinitely small, the event horizon of a black hole, to the structure of the infinitely large. It showed us that even in the vast, seemingly empty spaces between galaxies, the echoes of a past cataclysm still resonate, a silent witness to a universe far more energetic and dynamic than we once believed. The cavity in the Ophiuchus cluster is a lingering question, a reminder that the universe holds secrets far more profound than we can imagine. The discovery in Ophiuchus was not greeted with celebration, but with doubt. When the first data appeared, scientists did not believe what they saw. The cavity, stretching across 1.5 million light-years, seemed impossible. It was too vast, too cleanly carved, too demanding of energy. No model of black hole behavior predicted such a scar. For months, the whispers in the data were quietly set aside, consigned to the growing catalog of anomalies that must be explained by error. Astronomers had seen cavities before, structures left by the jets of supermassive black holes. In clusters like Perseus and Hydra A, these voids measured tens of thousands of light-years across. Enormous by human standards, but still comfortably within the limits of theory. Ophiuchus was different. This cavity was 15 times larger than any known before. To accept it as real meant rewriting the boundaries of what black holes could do. At first, scientists assumed the instruments had been fooled. The Chandra X-ray Observatory, circling Earth since 1999, is exquisitely sensitive to the faintest glows of plasma. But like all machines, it has limits. A shadow of background noise, a quirk of calibration, or the alignment of gas clouds could easily mimic a feature that wasn't truly there. The thought that a black hole could punch a hole larger than our entire galaxy cluster into the surrounding medium seemed absurd, but the data persisted. When XMM Newton confirmed the shape and radio telescopes traced the ancient shock front, the illusion hardened into fact. Ophiuchus had endured an outburst so violent that no comparison seemed adequate. The numbers told the story. The energy required to gouge out the cavity was estimated at 5 times 10 to the power of 61 ergs. Put differently, this was hundreds of millions of times more powerful than a supernova. It was thousands of times greater than the most energetic gamma-ray bursts, which themselves shine brighter than entire galaxies. If one were to gather the combined light of every star in the Milky Way, it would not rival the outburst in Ophiuchus. For a brief moment in cosmic time, one black hole had outshone the collective power of the universe around it. To call it an explosion is only approximation. Black holes do not detonate in the way stars do. They release energy through the conversion of falling matter, gas spiraling toward the event horizon, accelerated to relativistic speeds, twisted into jets by magnetic fields, and hurled back into the cosmos. Yet even in this framework, the scale of Ophiuchus was staggering. The amount of matter that must have fallen in, the efficiency with which it was converted into energy, the persistence of the jets across millions of years, all exceeded the expectations of physics as it was understood. Here, the rules began to tremble. For decades, astrophysicists had worked within boundaries, black holes of certain masses, accretion rates within certain limits, jet powers constrained by known physics. These principles were not arbitrary. They were drawn from observation and from equations that matched what was seen. But Ophiuchus lay beyond those boundaries. It was not merely a record-breaking event. It was an outlier so extreme that it destabilized the models themselves. If black holes could erupt with this violence, how often did it happen? Was Ophiuchus a singular anomaly, or had similar eruptions scarred clusters across the universe, waiting to be discovered? And if such outbursts were more common than imagined, what did that mean for galaxy evolution, for the heating of cosmic gas, for the balance of matter across time? The shock was not only in the numbers, but in the philosophy of science itself. For scientists, anomalies are the most dangerous discoveries. They carry within them the possibility that cherished theories may collapse. They open cracks in the foundations of knowledge. When the team led by Simona Giacintucci and Maxim Markovich published their results in 2020, the astronomical community was forced to confront these cracks. The eruption in Ophiuchus was not simply larger than anything recorded. It was so large that it defied the categories into which such events had been placed. A black hole was never thought to rival the energy of all galaxies combined. Yet here, it seemed to have done exactly that. The comparison unsettled even the most seasoned astronomers. To speak of energy on scales beyond trillions of supernovae was to step into a language of extremes, where metaphors collapsed and numbers lost meaning. It was not just the size of the cavity, but the fact that the explosion should not have been possible under the limits of known physics. Some wondered whether Ophiuchus pointed to an unknown mechanism, a hidden channel by which black holes can release energy more efficiently than previously believed. Others questioned whether the eruption represented a rare convergence of circumstances, a massive supply of gas, perfectly aligned magnetic fields, a black hole in an unusual state of accretion. Whatever the cause, it was clear that the rules of astrophysics could not be assumed to be fixed. For the wider scientific world, this was the true shock. The universe had revealed an event that broke its own apparent boundaries. The frameworks that had explained galaxy clusters and black hole feedback for decades suddenly felt fragile. And yet, the discovery carried an unsettling beauty. In the silence of Ophiuchus, astronomers were reminded of the humility required to study the cosmos. Theories are scaffolds, not walls. They are built to fit what is known, but they are never final. Beyond them lies the uncharted, where surprises wait. The Ophiuchus eruption was one such surprise, a whisper from the universe that even its most destructive forces had not yet been fully measured. In the coming years, telescopes would continue to search for other cavities, other scars in the plasma of clusters. Each new discovery would be measured against Ophiuchus, and none would match its scale. The event remained singular, a monument to the unpredictability of black holes. And so, the shock endured. The numbers stood unchallenged. The models trembled, but held. The cavity in Ophiuchus remains, a reminder that the universe does not conform to human expectation. It reveals itself only in fragments, each one rewriting what came before. The explosion should not have been possible, and yet it was. And in that contradiction lies the true mystery, a universe both knowable and unknowable, a cosmos whose rules bend under pressure, waiting for the next revelation to shake them again. In the established frameworks of astrophysics, the universe is governed by a set of predictable, albeit powerful, physical laws. These principles dictate the life cycle of stars, the dynamics of galaxies, and the theoretical limits of cosmic phenomena. However, observations can sometimes uncover events so extreme they challenge the very foundations of these models. Such was the case with the discovery of an unprecedented cataclysm in the Ophiuchus galaxy cluster, an event that has forced a profound re-evaluation of the most energetic processes in the cosmos. Located approximately 390 million light-years from Earth, the Ophiuchus cluster is a dense metropolis of thousands of galaxies enveloped in a vast cloud of superheated gas, known as the intracluster medium. While conducting surveys of this region, astronomers using NASA's Chandra X-ray Observatory noted a peculiar feature: a vast concave boundary in the hot gas. This feature delineated an enormous cavity, a near-perfect bubble of emptiness large, enough to contain 15 Milky Way galaxies. The initial reaction within the scientific community was one of deep skepticism. In observational astronomy, an extraordinary claim requires extraordinary evidence, and the most parsimonious explanation for such an anomaly is often instrument error. The data was rigorously scrutinized under the assumption that the cavity was an artifact, perhaps a glitch in the X-ray detectors, a software bug in the data processing pipeline, or some unforeseen calibration issue. Teams from around the globe embarked on the painstaking process of verification, reanalyzing terabytes of raw data and cross-referencing observations. However, the anomaly persisted. Subsequent analysis, incorporating data from radio telescopes, such as the Murchison Wide Field Array, NWA in Australia, and the Giant Meter Wave Radio Telescope, GMRT in India, confirmed the cavity's existence beyond any reasonable doubt. The radio data revealed the faint, aged emissions of electrons accelerated to near-light speed, tracing the precise outline of the X-ray void. The feature was not a ghost in the machine. It was a real, physical scar carved into the fabric of the galaxy cluster. With its existence confirmed, the focus shifted to the cause. The sheer scale of the cavity implied an energy release of almost inconceivable magnitude. To excavate such a volume from the dense intracluster medium would require a titanic explosion. Astrophysicists began the calculations, and the results were staggering. The energy required was estimated to be 5x 1055 joules. To place this figure in context, The standard unit for measuring extreme cosmic events is the supernova, the explosive death of a massive star. A single supernova can briefly outshine its entire host galaxy, releasing more energy in seconds than our Sun will in its 10 billion-year lifetime. The Ophiuchus event was not merely more powerful than a supernova, it was hundreds of millions of times more energetic. It represents the single most powerful explosion detected in the universe since the Big Bang. The total energy output rivals that of all the stars in all the galaxies in the observable universe at any given moment. This finding presented a direct challenge to the standard models of astrophysics. The only plausible culprit for such a release of energy was the supermassive black hole, residing in the cluster's central galaxy. Through the process of accretion, black holes draw in surrounding matter, which forms a swirling, superheated disk. This process is not perfectly efficient, and a significant fraction of the infalling matter can be redirected into powerful relativistic jets, collimated beams of plasma ejected from the black hole's poles at nearly the speed of light. These jets are known to blow bubbles or cavities in the surrounding gas. Yet there are theoretical limits to this process. The Eddington limit, a fundamental principle of accretion physics, dictates the maximum rate at which a black hole can consume matter. If a black hole feeds too voraciously, the outward pressure of the radiation it emits will halt the inflow of more material, effectively acting as a self-regulating throttle. The energy output seen in the Ophiuchus cluster shattered, this known limit suggesting a black hole had somehow unleashed an eruption far beyond its theoretical maximum capacity. It was as if a nuclear power plant had detonated with the force of a global-scale asteroid impact, a failure mode that should not be possible under its known design principles. The discovery has thus triggered a paradigm shift in our understanding of black hole feedback mechanisms. It indicates that our models are incomplete, and that under certain conditions, black holes can enter a state of extreme eruptive activity, far exceeding anything previously thought possible. The rules that were thought to govern the most massive objects in the universe were not just bent, but broken. The Ophiuchus cavity remains a silent testament to a force that defies explanation, compelling scientists to return to their theories and ask what fundamental aspect of the universe they might have overlooked. The cosmos speaks in many voices, but rarely in the visible light our eyes can see. To uncover its deepest scars, astronomers must turn to instruments that read the universe in other tongues: X-rays, radio waves, infrared, and beyond. Each wavelength is like a lantern shining into hidden corners of creation where the ordinary eye would see nothing at all. When the mysterious cavity was first glimpsed, it appeared as an absence, a vast hollow in the hot gas of a galaxy cluster, as though some colossal hand had scooped matter away. But to understand the violence that had carved this wound, scientists called upon their most sensitive instruments. The Chandra X-ray Observatory gazed into the void. Against the glowing plasma that fills clusters of galaxies, Chandra revealed a gaping dark region where the normal X-ray brilliance had been displaced. This was no ordinary fluctuation, no random turbulence. It was a hole, precise and immense, surrounded by ripples in the gas like frozen waves on an ancient sea. These ripples, scientists suspected, were the echoes of an unimaginable explosion. But the X-rays alone told only part of the story. Astronomers then turned to the quiet whispers of radio waves. From the Murchison Wide Field Array in Australia and the Giant Meter Wave Radio Telescope in India, faint radio emissions emerged from within the cavity. These signals betrayed the presence of relativistic particles. Electrons accelerated to near light speed, still spiraling in magnetic fields, long after the outburst that had hurled them outward. Where the X-rays had shown absence, the radio waves revealed persistence, the lingering smoke of a cosmic fire. Layer by layer, a picture began to form. The cavity was not empty at all, but filled with a ghostly radio glow, the remnant of a jet unleashed from the central black hole of a galaxy nestled within the cluster. That black hole, a gravitational pit millions of times more massive than the Sun, had once awakened in a violent outburst. With titanic force, it had funneled matter and energy outward in narrow jets, tunneling through the surrounding gas and blasting open a void of almost unimaginable proportions. To grasp its immensity, one must compare it to familiar scales. This single cavity, a scar in intergalactic space, was so large it could contain not one, but several entire Milky Way galaxies. Imagine our galaxy, with its hundreds of billions of stars, floating comfortably within this hollow, and still there. Would be room left over for others. What was once thought to be a faint irregularity in the cluster's X-ray glow was revealed instead as one of the largest known structures ever sculpted by a single galaxy's central engine. Then came the measurement that deepened the awe. Astronomers calculated the energy required to excavate such a void. The result was staggering. The outburst had unleashed an amount of energy equivalent to hundreds of millions of gamma-ray bursts. Each gamma-ray burst is among the most violent explosions known in the universe, often outshining entire galaxies for brief moments. Yet this single black hole event exceeded their combined fury, sustained not in a flash, but in a relentless surge of power over tens of millions of years. The discovery transformed a hollow shadow into a revelation. The cavity was no passive gap, but a scar left by cosmic violence on a scale almost beyond comprehension. It bore silent testimony to the hidden power of black holes, not merely destroyers, but architects, reshaping the very fabric of galaxy clusters, stirring their gas, and influencing the fate of galaxies that dwell within. Through X-rays, through radio waves, through the language of light invisible to human eyes, the universe had whispered its secret. And humanity, listening with patient instruments, had finally begun to understand. The story of the cosmos is not written in a single language. To human eyes, the heavens shine only in the faint glimmers of visible light, but that narrow band is a fragment of the truth. Beyond it stretches a spectrum vast and varied. Radio waves, infrared, ultraviolet, X-rays, and gamma rays, each carrying a different song of the universe. Where one instrument sees silence, another reveals a symphony. The great cavity discovered, in the Perseus cluster, an emptiness so vast it defied immediate explanation, demanded this multi-wavelength approach. To unravel its mystery, astronomers had to listen to the cosmos in all its registers, as though reconstructing a melody by gathering notes scattered across an infinite scale. The X-ray eyes of Chandra began with Chandra, the orbiting X-ray observatory that peers into realms invisible to optical telescopes. Galaxy clusters, those sprawling cities of galaxies bound together by gravity, are not empty space. They are suffused with gas heated to tens of millions of degrees, glowing in X-rays far brighter than invisible light. Through Chandra's gaze, the Perseus cluster revealed a luminous ocean of plasma, turbulent and restless, and there, within it, yawned the void, a cavity cut into the glow like a shadow in firelight. Its shape was smooth, defined, too deliberate to be random chaos. Around it rippled concentric waves, faintly reminiscent of the ripples on a pond after a stone is thrown. Except here the stone was never seen, and the pond stretched across hundreds of thousands of light years. These ripples told a story. They were not static patterns, but echoes of pressure waves, sound waves, traveling through the cluster's gas. If our ears could hear at frequencies trillions of times lower than human perception, we would hear the song of the cluster, a deep cosmic note resonating across space for hundreds of millions of years. The cavity was its drumbeat, struck by a force that dwarfed imagination. The whisper of radio waves, but X-rays alone could not explain the scar. They showed the wound, but not the weapon. To uncover its cause, astronomers turned to instruments that capture the faintest radio emissions. The Murchison Wide Field Array in Australia and the Giant Meter Wave Radio Telescope in India opened their vast ears to the cosmos. At first, the cavity appeared silent. Yet, with patience and careful analysis, a ghostly glow emerged within the hollow. It was the telltale signature of synchrotron radiation, the spiraling dance of high-energy electrons caught in magnetic fields, releasing their energy as radio waves. This was no accident of nature. These particles had been hurled outward at near-light speed, relics of a colossal jet launched from a supermassive black hole at the heart of the cluster's brightest galaxy. Where X-rays had shown emptiness, radio waves revealed persistence. The cavity was not devoid of matter, but filled with the faint afterglow of an ancient eruption, like smoke lingering long after the fire has gone. The jet that carved a universe-sized scar. The culprit came into focus, the central black hole, a gravitational behemoth millions of times the mass of the Sun. Ordinarily, a black hole swallows matter, its gravity so absolute that even light cannot escape. But paradoxically, when a torrent of gas and dust falls inward, some of it is transformed into energy, channeled into beams narrower than a galaxy, yet longer than intergalactic space. These are relativistic jets, streams of plasma moving so close to the speed of light that time itself slows for the particles within them. Such a jet had burst forth from the Perseus black hole millions of years ago. With unstoppable force, it plowed into the cluster's atmosphere, driving gas outward, excavating a hollow the size of multiple galaxies. Over tens of millions of years, the jet faded, but the scar remained, a monument to the violence of invisible engines at the hearts of galaxies. The scale of the void, to imagine its size, is to attempt the impossible. The cavity could engulf several Milky Ways, our own galaxy with its swirling arms of hundreds of billions of stars, and still leave space unused. It is a structure so vast that light, the fastest traveler in the cosmos, would take hundreds of thousands of years to cross from one side to the other. We are accustomed to thinking of galaxies as the grandest of scales, But here, a single black hole has reshaped a region so large that galaxies become mere furniture within its vast interior. These, energy of a monster. The true astonishment came when scientists measured the energy required to create such a cavity. The number they found staggered belief. The eruption released more energy than hundreds of millions of gamma-ray bursts combined. A gamma-ray burst, by itself, is one of the most ferocious events in the universe. A dying star collapsing, a black hole forming, a flash that can briefly outshine all the stars of a galaxy. But this black hole outburst dwarfed them not in a sudden blaze, but in sustained fury. It poured its might into the surrounding space for tens of millions of years, carving and shaping, sculpting matter on cosmic scales. It was as though nature had revealed a new category of violence. Not the quick death of a star, but the long, slow rage of a black hole, altering the destiny of entire clusters. A scar that shapes galaxies, yet the cavity is more than a scar. It is a force of influence. The energy that dug this void did not vanish into emptiness. It stirred the cluster's gas, slowed the cooling of plasma that might otherwise condense into new stars, and in doing so, it regulated the growth of galaxies. Black holes, once thought to be passive consumers, are revealed as cosmic regulators, their outbursts dictating the balance of creation itself. Without their feedback, clusters might collapse into waves of unchecked star formation. Instead, they live in a delicate equilibrium, maintained by explosions so vast they echo across hundreds of millions of light years. Reflection, the silence of violence in the stillness of the cavity lies a paradox. It is a monument to destruction, yet it ensures creation continues in measured form. It is a scar, yet also a heartbeat. The Perseus cavity reminds us that black holes are not merely engines of doom, swallowing stars into oblivion. They are sculptors of galaxies, guardians of balance and keepers of secrets that ripple across the grandest scales. Through the eyes of Chandra, through the ears of Murchison and GMRT, through the language of invisible light, humanity glimpsed the traces of an event that dwarfs every human conception of power. And in that glimpse the universe whispered a truth. Even in its most violent acts there is order, rhythm, and meaning written across the canvas of eternity. An immense ocean of silence. That's how we once pictured the space between galaxies, a static, silent void stretching across millions of light years. But this emptiness, we've come to understand, is an illusion. The space between galaxies is not a vacuum. It is filled with a thin, tenuous gas, a superheated plasma that carries the whispers of cosmic history. Within this medium, the intracluster medium, astronomers discovered a chilling secret, the Ophiuchus cavity. The finding itself was dramatic, but it was the scale of the event that sent a tremor through the world of astrophysics. This was not a scar left by a single supernova. 1,000, even 1,000,000 stellar explosions would not have been enough to displace so much gas. No, the sheer size of the cavity was a testament to a force so powerful It had literally carved out a section of the intracluster medium. Its size was so vast it defied all previous observations. The initial reaction was one of disbelief. Astronomers, who first analyzed the data from the Chandra X-ray Observatory, questioned everything. Could this be a glitch? An error in the sensor? An uncorrected anomaly in the data processing? The cavity was simply too large, its implications too profound. The energy required to create such a void was staggering, hundreds of millions of times the energy of a typical supernova. To put that into perspective, a single supernova can outshine an entire galaxy. What kind of cosmic engine could produce a blast hundreds of millions of times more powerful than that? The answer pointed to the supermassive black hole at the heart of the galaxy, the most powerful cosmic engine known. But this created an even greater problem. Under standard models, even the most active black holes are not thought to be capable of such an outburst. The rules were trembling. For decades, our understanding of black holes was that they could launch powerful jets from their poles, but the Ophiuchus explosion suggested a level of sustained energy output that was, by all accounts, impossible. This was more than a discovery. It was a crisis. The very models that helped us understand galaxy formation and evolution were suddenly under question. The explosion was so powerful, it rivaled the combined energy output of all the galaxies in the universe for a time. It forced scientists to reconsider the role of black holes. No longer were they merely passive devourers. They were active, dynamic architects of their cosmic neighborhood, capable of shaping the very universe around them. The ghost of the explosion, the Ophiuchus cavity, became a silent testament to a cosmic battle far greater than we had imagined. It revealed that in the vast, seemingly placid cosmos, forces of incomprehensible violence are at play, forces that are capable of defying our most fundamental laws and reminding us how little we truly know. For an event of this magnitude to occur, a black hole would have to be consuming matter at an unprecedented rate. The process is not about the black hole's gravity, but about the incredible energy released as material in the accretion disk spirals inward. The immense friction and powerful magnetic fields in this swirling disk accelerate particles to nearly the speed of light, channeling them into focused jets that are then launched into space. The Ophiuchus event demanded a level of sustained energy output that was simply not thought to be possible for a black hole of that size. This led to a host of new, mind-bending theories. What if the black hole at the center of the Ophiuchus cluster wasn't simply devouring a large cloud of gas? What if it was something far more dramatic? One tantalizing theory is that the event was triggered by the merger of two supermassive black holes. The collision of these cosmic titans would have been an event of unimaginable violence, releasing gravitational waves that would have rippled across the universe. The newly formed, even more massive black hole would have been left spinning at an incredible rate with a newly formed accretion disk of immense size and power. This violent, chaotic beginning could have provided the sustained, colossal energy needed to create the jets that carved out the Ophiuchus cavity. Whether it was a massive feeding frenzy or a violent merger, the implications were the same. Our existing understanding of black hole physics was incomplete. The universe, it seemed, was capable of acts of violence far beyond our imagination. This discovery was not just a curiosity, it solved a long-standing mystery. For years, scientists had wondered what prevented gas in galaxy clusters from cooling and collapsing to form new stars. The Ophiuchus cavity provided a powerful answer. The energy from the black hole's explosion acted as a cosmic thermostat, keeping the intracluster medium at a searing temperature. This prevented gas from condensing and forming new stars effectively, or shutting down star formation in the core of the galaxy. It's a fundamental process of cosmic evolution, a hidden feedback loop that has shaped the universe for eons. The Ophiuchus cavity is the first direct and undeniable evidence of this process on such a massive scale. The universe, we are learning, is not a calm, predictable place. It is a place of extremes, of forces so immense that they can defy our most fundamental laws and shake the foundations of our understanding. The silent scar left behind in the Ophiuchus galaxy cluster is a testament to this, a powerful reminder that our models of reality are constantly evolving, and that the cosmos holds secrets far more profound than we can yet imagine. In the quiet reaches of intergalactic space, astronomers expected silence. But what they found instead was a roar so vast, it seemed to echo through the fabric of the cosmos itself. From the heart of a distant galaxy, a jet erupted, plasma flung, at nearly the speed of light, carving a wound across hundreds of thousands of light years. Jets like these are not strangers to science. They are the signatures of supermassive black holes, devouring matter and spitting out the excess in torrents of radiation and fire. But this was something different. The scale defied familiarity. It was not merely a black hole outshining its peers. This jet carried the energy equivalent of hundreds of millions of supernovae, an output so staggering that the galaxy itself should have been torn apart by its violence. Yet the host remained, intact, silent, still orbiting its stars, as if unaware of the storm raging at its center. Physicists strain to explain it. Conventional theory holds that jets are powered by the twisting magnetic fields around spinning black holes. The rotation, frame-dragging spacetime itself, channels infalling matter into narrow beams, launching them outward in collimated streams. But those equations have limits. The known mechanics of magnetism and angular momentum cannot account for a release of this magnitude. For this event to exist, something else must be at work. Something hidden in the deep architecture of space-time. It was as though the black hole had tapped into a reservoir larger than itself, an ocean of energy folded into the vacuum. The universe provides hints that such seas exist. Quantum field theory suggests that even empty space seethes with potential, the zero-point fluctuations of the vacuum. Could a black hole, under extraordinary conditions, pierce the veil, draining power not from matter, but from space-time itself? The thought lingers, unsettling. Because if this eruption was not born of simple accretion, but of the vacuum's hidden fabric, then the laws of physics as written are not yet complete. The event would not merely be an astrophysical curiosity, it would be a message, a signal that the cosmos conceals deeper mechanisms waiting to be unbound. Astronomers replay the images, studying every frame of data. The more they analyze, the less it behaves like anything expected. its symmetry, its coherence, the sheer stability of a jet so ferocious, yet so finely tuned, as though it were sculpted by unseen hands. It does not resemble chaos. It resembles design, though not in the human sense of intention, but in the deeper sense of cosmic order, written in mathematics yet unlearned, and so the mystery deepens. This was not just another black hole's heartbeat. It was a crescendo, beyond comprehension, the kind of phenomenon that whispers of unfinished science, a puzzle not only of energy, but of existence itself. The universe had opened a door, and with every calculation, every spectrum measured, every photon received across the abyss of time, one thing becomes clear. The more we study it, the stranger it becomes. The silent cavity in the Ophiuchus galaxy cluster, a scar in the fabric of space, was not just a discovery, it was a cosmic paradox. We had seen black holes launch jets before, streams of energy that can span hundreds of thousands of light years. But this was different. This was an act of violence so profound it defied the very models we had constructed to understand the universe's most powerful engines. The paradox was simple. How could a black hole, a mere point of infinite density, unleash an explosion that, by all accounts, should have torn its host galaxy to shreds? The jets from the central black hole of the Ophiuchus cluster had carved out a void that could swallow multiple Milky Ways. The energy released was equivalent to hundreds of millions of gamma-ray bursts, the most powerful explosions we know of in the universe. Such a sustained, colossal output of energy should have destroyed the delicate balance of the galaxy, stripping it of its gas and stars. Yet, the galaxy remains. It is a mystery that suggests a hidden layer of complexity to the cosmos. This was not just another big bang from a black hole. It was a blast that was staggering beyond the known range of anything we thought was possible. It forced us to confront the very limits of our understanding of energy, of gravity, and of space-time itself. For decades, the Eddington limit stood as a fundamental principle in astrophysics. It states that there is a maximum luminosity a celestial object can achieve before the outward pressure of its own radiation overwhelms its inward gravitational pull, effectively pushing away any additional matter. But the Ophiuchus event seemed to laugh at this limit, suggesting that a black hole could somehow bypass this cosmic speed limit and unleash a torrent of energy that should, by all rights, be impossible. The escalation of this mystery lies in its implications. What if the source of this power isn't just the black hole's feeding, but something more fundamental? Could it be a sign of a new, unknown type of physics at play? Could the black hole be drawing energy from an even deeper well, perhaps from the very nature of space-time itself? Some speculative theories suggest that the black hole might have been drawing on the energy of the false vacuum, a hypothetical state of the universe with a higher energy density, and that this immense power had been harnessed and released. It is an idea that is as terrifying as it is profound, suggesting that the universe we know could be a delicate state, and that black holes are not just engines of destruction, but cosmic keys capable of unlocking forces we cannot yet comprehend. The more we study the silent scar in the Ophiuchus cluster, the stranger it becomes. We measure its size, we calculate its energy, and we find that it contradicts our most fundamental laws. It is a cosmic paradox, a silent reminder that our understanding of the universe is still in its infancy. It is a story not just of a discovery, but of a confrontation with the unknown. The silent cavity in the Ophiuchus galaxy cluster, a scar in the fabric of space, was not just a discovery, it was a cosmic paradox. We had seen black holes launch jets before, streams of energy that can span hundreds of thousands of light years. But this was different. This was an act of violence so profound it defied the very models we had constructed to understand the universe's most powerful engines. The paradox was simple. How could a black hole, a mere point of infinite density, unleash an explosion that, by all accounts, should have torn its host galaxy to shreds? The jets from the central black hole of the Ophiuchus cluster had carved out a void that could swallow multiple Milky Ways. The energy released was equivalent to hundreds of millions of gamma-ray bursts, the most powerful explosions we know of in the universe. Such a sustained, colossal output of energy should have destroyed the delicate balance of the galaxy, stripping it of its gas and stars. Yet, the galaxy remains. It is a mystery that suggests a hidden layer of complexity to the cosmos. This was not just another Big Bang from a black hole. It was a blast that was staggering beyond the known range of anything we thought was possible. It forced us to confront the very limits of our understanding of energy, of gravity, and of space-time itself. For decades, the Eddington limit stood as a fundamental principle in astrophysics. It states that there is a maximum luminosity a celestial object can achieve before the outward pressure of its own radiation overwhelms its inward gravitational pull, effectively pushing away any additional matter. But the Ophiuchus event seemed to laugh at this limit, suggesting that a black hole could somehow bypass this cosmic speed limit and unleash a torrent of energy that should, by all rights, be impossible. The escalation of this mystery lies in its implications. What if the source of this power isn't just the black hole's feeding, but something more fundamental? Could it be a sign of a new, unknown type of physics at play? Could the black hole be drawing energy from an even deeper well? Perhaps from the very nature of space-time itself. Some speculative theories suggest that the black hole might have been drawing on the energy of the false vacuum, a hypothetical state of the universe with a higher energy density, and that this immense power had been harnessed and released. It is an idea that is as terrifying as it is profound, suggesting that the universe we know could be a delicate state, and that black holes are not just engines of destruction, but cosmic keys capable of unlocking forces we cannot yet comprehend. The more we study the silent scar in the Ophiuchus cluster, the stranger it becomes. We measure its size, we calculate its energy, and we find that it contradicts our most fundamental laws. It is a cosmic paradox, a silent reminder that our understanding of the universe is still in its infancy. It is a story not just of a discovery, but of a confrontation with the unknown. The universe is not silent. Every so often, a galaxy trembles under a sudden outburst, an eruption from its central abyss, where a supermassive black hole waits like a heart of darkness. For decades, astronomers have struggled to answer a question that echoes through the void. What drives these titanic flares of energy? The theories are many. None are complete. Each opens a different doorway into the hidden machinery of the cosmos. Some scientists look first to the black holes themselves, not as passive consumers, but as regulators of galactic life. When matter falls too quickly into a supermassive black hole, it cannot all be swallowed at once. The core builds pressure, magnetic fields twist, and energy is released in catastrophic waves. These eruptions, lasting millions of years, push back against the galaxy that feeds them. Like a cosmic heartbeat, they regulate growth, preventing galaxies from collapsing under their own weight of stars. Without these feedback loops, simulations suggest that galaxies would be far denser, star formation far more chaotic. The black hole, in this vision, is less a destroyer than a gardener, burning away excess, pruning the galaxy into stability. Yet even here, mysteries remain. The timing is irregular, the violence unpredictable. Why some galaxies flare, while others slumber, is still an unanswered riddle. Another theory lies in the hidden architecture of magnetism. Magnetic fields are invisible threads, spun throughout the cosmos. In the furious environment around a black hole, these fields can twist into colossal spirals, whipping plasma into jets that span hundreds of thousands of light years. This is the realm of magnetohydrodynamics, a dance between gravity, plasma, and magnetic force. Here, energy is not released in quiet streams, but in sudden torrents, bursts capable of reshaping entire galactic halos. The mechanism is elegant yet perilous. Magnetic reconnection, where tangled fields snap and realign, unleashing more power than billions of suns combined. Still, magnetism alone cannot explain the full spectrum of eruptions. It answers how the energy escapes, but not always why it ignites. The accretion disk itself, the swirling sea of matter spiraling toward the event horizon, may hold the next clue. Disks are not stable places. Their structure trembles with turbulence, density waves, and thermal instabilities. When enough matter piles up, a runaway begins. Heat surges, radiation pressure skyrockets, and the disk erupts in a blaze that can outshine the galaxy around it. Some researchers liken these events to volcanic eruptions on Earth, quiet accumulation followed by violent release. But unlike volcanoes, these explosions are powered by the raw collapse of spacetime's steepest. Well, even this, however, leaves gaps. The cycles of accretion are difficult to predict, and observations suggest that some eruptions are far larger than such instabilities alone should allow. And then, the speculations grow darker. Some theorists whisper of deeper connections between these flares and the unseen forces shaping the universe at the largest scale. Dark energy, the enigmatic pressure that accelerates cosmic expansion, remains almost entirely unknown. Could the same hidden physics that drives galaxies apart also play a role near black holes? Could these eruptions be echoes of a deeper instability, one that links the smallest and largest scales of reality? The most unsettling possibility touches on vacuum instability, the idea that the universe itself rests in a false stability, a fragile state that could one day collapse. In this vision, a single fluctuation might trigger space-time to rupture, rewriting the laws of physics in an expanding bubble of destruction. Are the violent flares of galaxies a local rehearsal of this ultimate catastrophe, a warning written in light? Or are they simply the excess energy of matter devoured by gravity's abyss, with no greater meaning? The truth remains elusive. Each theory explains part of the story, yet none can claim the whole. Black hole feedback offers balance. Magnetohydrodynamics provide the mechanism. Accretion disk instabilities supply the spark, while dark energy and vacuum instability raise specters of a deeper unknown. In the end, the eruptions remain what they have always been: messages from the edge of understanding, signals written in bursts of radiation, carrying across millions of light years, asking the same question again and again. What truly is the universe made of? In the vast, uncharted reaches of the cosmos, where the silent roars of supermassive black holes ripple through the fabric of spacetime, humanity deploys its most intricate sentinels to capture the echoes of these titanic eruptions. These celestial outbursts, stretching across millions of years, sculpt galaxies with bursts of energy that balance creation and destruction, forging order from chaos. The mystery persists. How do these enigmatic giants, enthroned at galactic cores, regulate the cosmic dance of star formation? To unravel this, astronomers wield an arsenal of telescopes: Chandra's piercing X-ray gaze, XMM Newton's broad sweep, Rosita's panoramic vision, and the James Webb Space Telescope's infrared whispers, each probing the scars left by black hole feedback. Radio arrays trace the plasma trails of relativistic jets, while supercomputers weave digital tapestries simulating eruptions that unfold over eons. Future missions, like Athena and Lynx, promise to peer deeper, their advanced optics poised to unveil the subtle interplay of forces shaping the universe. This chapter, a meditation on humanity's tools and aspirations, explores the cutting-edge science of detecting events not in fleeting seconds, but across the slow, majestic arc of cosmic time, where each observation is a brushstroke on the canvas of eternity, reflecting the delicate balance between chaos and order, and humanity's relentless quest to touch the infinite. The Chandra X-ray Observatory, a sentinel orbiting Earth since 1999, pierces the veil of the cosmos with its high-resolution mirrors capturing X-ray emissions from the searing plasma of black hole jets. Its gaze, focused on galaxy clusters like Perseus, reveals vast cavities carved by active galactic nuclei, AGN, where relativistic jets inflate bubbles in the intracluster medium, heating gas to prevent runaway star formation. These cavities, glowing in X-rays, testify to feedback's power, a cosmic thermostat regulating galactic growth. Chandra's observations of M87's jets, stretching across tens of thousands of light-years, show how black holes sculpt their hosts, their energy outbursts echoing across millennia. The telescope's strength lies in its precision, resolving fine details of shock fronts and hot spots, yet its narrow field limits its view of broader cosmic landscapes. Philosophically, Chandra embodies humanity's desire to see the unseen, its X-ray eyes peering into the heart of chaos, where destruction fosters structure, a mirror to the human struggle to find meaning in turmoil. XMM Newton, launched by the European Space Agency complements Chandra with its wider field of view, capturing the diffuse glow of galactic clusters and the faint traces of AGN feedback. Its spectrographs dissect X-ray emissions, revealing the chemical fingerprints of heated gas enriched with metals forged in stellar furnaces. In the Coma cluster, XMM Newton's maps show turbulent wakes left by black hole jets, their energy dispersing gas to temper star birth. The telescope's ability to survey large swaths of sky makes it a cartographer of cosmic scars. Yet its lower resolution blurs finer details, leaving gaps in the narrative. Speculatively, XMM Newton's data hints at feedback cycles linked to dark energy fluctuations, a notion explored in recent theoretical models, suggesting black holes may subtly influence cosmic expansion. Emotionally, XMM Newton's broad gaze evokes a cosmic elegy, capturing the slow fade of galactic vitality, a reminder of time's relentless march and humanity's fleeting place within it. Rosita, aboard the Spectre RG mission since 2019, paints a panoramic portrait of the X-ray sky, mapping millions of AGN across billions of years. Its all-sky surveys reveal the evolution of black hole activity from the quasar-dominated early universe to today's quieter galaxies. In clusters like Abell 2029, eRosita's sensitive detectors trace feedback-driven bubbles, their edges glowing with the heat of past eruptions. The telescope's strength lies in its breadth, offering a cosmic census that links black hole activity to galaxy formation across epochs. Yet, its resolution cannot match Chandra's precision, leaving some mysteries unresolved. Credibly, eRosita's data could reveal correlations between AGN outbursts and large-scale structure, potentially unveiling dark matter's role in amplifying feedback. Reflectively, eRosita mirrors humanity's ambition to map the cosmos's history. It surveys a tapestry of light and shadow, weaving the story of galaxies shaped by unseen forces. The James Webb Space Telescope, JWST, orbiting 1.5 million kilometers from Earth, brings infrared vision to this cosmic quest, its golden mirror capturing light from the universe's dawn. JWST's mid-infrared instrument, cooled to a frigid 6.7 Kelvin, peers through dust clouds, revealing accretion disks around black holes in galaxies like NGC 4151. Its spectra uncover the dynamics of gas inflows, fueling outbursts that regulate star formation. In ultraluminous infrared galaxies, JWST's 2025 observations show merger-driven disks sparking AGN activity, their infrared glow a testament to feedback's power. The telescope's strength lies in its ability to probe obscured regions, yet its focus on specific targets limits its survey scope. Speculatively, JWST could detect infrared signatures of dark energy-driven expansion in AGN environments, linking micro-scale outbursts to cosmic acceleration. Philosophically, JWST's gaze evokes a poetic longing, its light piercing the cosmic veil to reveal the delicate interplay of creation and destruction, a mirror to humanity's search for origins in the infinite dark. Radio arrays, like the Very Large Array and the Square Kilometer Array's precursor, MeerKAT, trace the plasma scars of black hole jets, their radio waves mapping relativistic outflows across cosmic distances. In Cygnus A, MeerKAT's high-sensitivity maps reveal lobes stretching hundreds of thousands of light-years, their synchrotron emissions tracing magnetic fields twisted by magnetohydrodynamic forces. These arrays excel in capturing the large-scale impact of feedback, their wide fields charting the cosmic web's filaments and voids. Yet their resolution struggles with the fine details of accretion disks, leaving inner dynamics to other instruments. Speculatively, radio arrays could detect low-frequency signatures of primordial magnetic fields, amplifying jet power, a hypothesis rooted in recent theoretical models. Emotionally, these arrays evoke a cosmic symphony, their signals a chorus of ancient eruptions resonating across time to remind us of the universe's enduring pulse. Supercomputer simulations weave these observations into digital tapestries, recreating black hole eruptions with breathtaking fidelity. Projects like Illustrious TNG and Eagle use numerical relativity to model gas dynamics, magnetic fields, and feedback cycles, simulating galaxies over billions of years. These codes, running on clusters like those at the Max Planck Institute, solve equations of general relativity and hydrodynamics, capturing the interplay of accretion and outflows. In simulations, AGN jets inflate cavities, matching Chandra's. Observations while accretion disk instabilities trigger bursts echoing JWST spectra. The strength of simulations lies in their predictive power, testing theories against observed data. Yet they falter in computational limits, simplifying complex physics like turbulence or quantum effects. Speculatively, future simulations could incorporate dark energy dynamics, modeling feedback's impact on cosmic expansion, a frontier explored in recent Arxiv preprints. Philosophically, these simulations mirror humanity's attempt to recreate the cosmos, a digital reflection of the universe's chaos, seeking order in lines of code. Future missions, like Athena and Lynx, promise to deepen this quest. Athena, set for launch in the 2030s, will wield advanced X-ray spectrographs, resolving feedback-driven shocks with unprecedented clarity, potentially unveiling dark matter's role in jet propagation. Lynx, a proposed X-ray observatory, aims to map sub-parsec scales near black hole event horizons, probing accretion disk dynamics. Both missions could detect subtle signatures of vacuum instability, where extreme gravity nudges space-time toward collapse. Their strength lies in their technological leap, yet their speculative nature, awaiting confirmation, tempers certainty. Credibly, they could link feedback to large-scale structure, revealing cosmic forces unseen. Emotionally, these missions evoke a cosmic pilgrimage, humanity's gaze stretching toward the unknown, seeking answers in the silent scars of ancient eruptions. The science of detecting these explosions, unfolding not in seconds but across millions of years, is a testament to humanity's patience and ingenuity. Unlike terrestrial blasts, black hole outbursts stretch across cosmic timescales, their energy dispersing slowly through galactic halos. Chandra's long-term monitoring of M87 shows jet variability over decades, hinting at cycles spanning millennia. Simulations suggest feedback loops persisting for millions of years, matching Rosita's cluster maps. This slow cadence evokes a cosmic rhythm where time's vastness dwarfs human perception, yet each observation, a snapshot of eternity, builds the narrative. The mystery endures. How do these eruptions, born in chaos, forge galactic order? As telescopes and simulations probe deeper, the cosmos reveals a tapestry of balance and upheaval, where black holes, both destroyers and creators, mirror humanity's eternal quest for meaning in the infinite night. In the vast cathedral of the cosmos, where stars are but candles flickering against the eternal dark, there exists a violence so profound it defies the boundaries of human comprehension. Imagine for a moment the sun, its roiling surface, a cauldron of plasma, its light the lifeblood of Earth, erupting in a cataclysmic supernova. The Earth would not merely burn, it would dissolve, its oceans boiled to vapor, its mountains reduced to ash in an instant. Yet, even this apocalyptic vision pales, a mere whisper against the tempest of the most violent explosion ever witnessed in the universe. If every star in the Milky Way, all 100 billion, were to detonate in unison, their combined fury would still fall short of the cataclysm born from the collision of two black holes, an event so colossal it sends ripples through the very fabric of spacetime. This explosion, detected by humanity's delicate instruments as a fleeting gravitational wave, is no mere spectacle. It is a testament to the universe's capacity for creation through destruction, a paradox woven into the essence of existence. Black holes, those silent sovereigns of the cosmos, are defined by their absence, lightless, soundless, invisible. They are the ultimate enigma, devouring matter and time itself, leaving only the weight of their presence. Yet, from their mute dominion comes a violence that roars across galaxies. When two black holes, each a collapsed remnant of a star long, dead, spiral toward one another in a cosmic dance, their union births a maelstrom. Their collision, a fleeting moment spanning mere milliseconds, releases energy equivalent to billions of suns, a scream etched into the universe's geometry, felt by observatories like LIGO as a tremor in the fabric of reality. Consider the scale. Humanity's greatest wars, with their fire and steel, their cities reduced to rubble, are but fleeting sparks in the shadow of this event. The infernos that have scarred Earth's history, volcanic eruptions, meteor strikes, the slow burn of continents adrift, are mere embers compared to the incandescent fury of merging black holes. The energy unleashed in such an event could power civilizations for eons, yet it is spent in an instant, a cosmic exhale that reshapes the heavens. The gravitational waves that reach us, faint as a whisper across billions of light-years, carry the story of this violence, a story written not in light or matter, but in the warping of space-time itself. What does it mean that black holes, these silent devourers, are capable of such deafening chaos? They are the universe's great contradiction, objects of infinite density, where time slows to a crawl, yet catalysts for events that ripple outward at the speed of light. In their collision, they do not merely destroy, they create. The merger of two black holes forms a new singularity, a fresh wound in the cosmos, its mass greater than the sum of its parts. This act of union, violent though it is, seeds the universe with new possibilities, perhaps new orbits, new stars, new worlds, born in the wake of destruction. It is as if the universe, in its relentless churn, insists that no end is final, that every collapse is a prelude to rebirth. This explosion, this singular event, forces a reckoning with humanity's place in the grand tapestry. Earth, a fragile mote suspended in the cosmic sea, is but a speck against the scale of such forces. The wars that divide nations, the fires that consume forests, the ambitions that drive empires, all are rendered infinitesimal before the universe's relentless power. Yet, there is a strange humility in this realization, a quiet awe that binds humanity to the cosmos. For in observing these events, in detecting the faint echoes of black hole mergers, humanity reaches out to touch the infinite. The instruments that capture these waves, LIGO, Virgo, and their successors, are not merely machines. They are extensions of human curiosity, fragile tendrils stretching toward the unknowable. Are such explosions rare, or are they the heartbeat of the universe, pulsing ceaselessly across its vast expanse? The data suggests they are not uncommon. Gravitational wave observatories have detected dozens of black hole mergers since the first in 2015, each a testament to the universe's turbulent history. Some theories propose that such events are woven into the cosmos's fabric, occurring wherever massive stars die and collapse, their remnants drawn inexorably together by gravity's unyielding pull. Others speculate that the early universe, dense and chaotic, was a crucible for such collisions, with primordial black holes merging in a frenzy of creation and destruction. The truth, as always, lies just beyond reach, a shadow dancing at the edge of understanding. Is the universe itself balanced on cycles of violent release? The question lingers, heavy with implication. Stars are born in the fiery crucibles of nebulae, only to die in supernovae that seed the cosmos with the elements of life. Galaxies collide, their spiral arms entwining in a slow, majestic waltz that spans millions of years, birthing new stars even as others are torn apart. Black holes merge, their union a spark that reshapes spacetime. Everywhere the universe seems to thrive on this duality, creation and destruction, order and chaos entwined in an eternal dance. To witness such an explosion is to glimpse this cycle in its rawest form, a reminder that the cosmos is not a static painting but a living story, written in fire and gravity. Could such an event reshape the cosmos in ways yet unimagined? The ripples of a black hole merger do more than carry energy. They alter the structure of space-time itself, bending the paths of light and matter across vast distances. In the far future, as observatories grow more sensitive, humanity may map these ripples with precision, tracing their effects on distant galaxies, on the formation of stars, on the very evolution of the universe. Perhaps such events hold the key to mysteries still unsolved: the nature of dark matter, the origin of the universe's accelerating expansion, or even the possibility of other dimensions hidden in the folds of space-time. The collision of black holes may be a window into these unknowns, a fleeting glimpse of truths too vast for the human mind to fully grasp. The most violent explosion in the history of the universe is not just a scar in the sky. It is a reminder that creation and destruction are one, that the cosmos is a tapestry woven from threads of chaos and order. As humanity gazes upward, charting the faint echoes of these cataclysms, it confronts its own impermanence, its own fleeting place in the grand narrative. Yet, in that confrontation lies a profound truth. To witness the universe's violence is to share in its story, to stand, however briefly, at the edge of the infinite. And in the silence that follows, as the ripples fade into the cosmic dark, the universe continues to write its tale, one of fire, of gravity, of endings that are beginnings, and of mysteries that endure.